So I want to qualify the comment about the guitarist first because I feel a little embarrassed. It sounds really like bold and amazing saying that you've made two guitars. I made two guitars from kits. They were decent kits. There was a lot of work. I really highly recommend the process. Actually, if you have the slightest interest, go for it. It's a lot of fun, but do be prepared for some frustration as well. Um, so like Richard mentioned, please do ask questions anytime. My goal with this discussion is for it to be fairly informal, treating it a little bit like a brown bag lunch or something like that. If you're not familiar with that term, it's a group of colleagues. You want to share something that you've learned with your colleagues. That's about all. Likewise, these, like Nadia said, I can see those here. I don't have to be looking over my shoulder. There we go. Likewise, the six in no particular order comments, these are things that I'm going to chat about if questions don't supersede them. So don't feel like you have to ask questions either. If you don't force yourself to think up something if you haven't already. I will keep talking regardless. So yeah, in addition to being the lead of the semantic project at GitHub, and in fact, as part of that process, I am the primary author and primary maintainer of the fused effects package on Hackage. Fused effects is an algebraic effects and handlers package embedding effects and handlers in Haskell. It's pretty cool how it works. It's based primarily on work by Nick and Tom. Nick and Tom's work first was involved in the use of scoped effects, so effects that aren't strictly algebraic, but rather range over some other computation. You can think of it as maybe bookending that computation with some other calculation on either end. You can't do this with just algebraic effects because algebraic effects are required. The thing that makes them algebraic is that they commute with the continuation, with the bind, which means that if you have an operation with some arguments and then bind some continuation after it, it's the same thing as doing the operation having bound the continuation on each of those arguments to begin with. This is not the case for something like catch. So with catch, you're scoping over some computation that you want to check for exceptions having been thrown within, and then you're going to pass any such exceptions to the handler. It's clearly not an algebraic operation, and there turn out to be many such. If you're familiar with the reader monad, local is another such scoped operation. And it may seem a little bit esoteric or even academic distinction to make, but it turns out to be really important in practice, which is what we learned in the development of semantic, which is what led to fused effects. So the second thing that led to fused effects was just efficiency. We had based an earlier effect system on the extensible effects work, which was really, really cool that we were able to do this. Like it blew our minds, frankly, that we were able to just build this thing, drop it into a Haskell project, and boom, we've made an effect system. We knew that Haskell was a very programmable language, but we didn't really anticipate it being that easy to just sit down and make this thing that gives us a strata for doing simulating effects of all sorts. That was pretty fantastic. But when we extended it to use scoped effects, we ran into some pretty significant problems with efficiency. Or I should say, once we had done that. Turns out that the lack of scoped effects in our initial implementation was just the first of a series of challenges that we had faced. So then, having scoped effects in this thing, having run into some performance challenges, we then turned to the challenge of integrating another of Nick and Tom's piece of Nick and Tom's research, the Fusion for Free paper, which if you haven't read, it's really magical. One model for understanding how effects can be understood in a programming language like Haskell, or just in general, actually, is free monads. The idea is basically that a free monad gives you some signature of operations, effectful operations that can be performed, and then also gives you the ability to say, here's a free variable or a result, however you want to look at it, and bind these together into a chain of different computations, chain of statements, one after the other after the other. So the embedding of a free monad like that is a cool trick. It's like the precursor to the extensible effects approach of doing the same work, but again has some efficiency problems. So if you apply the Fusion for free approach, what you do is you take a series of handlers. Each one is kind of a fold over that structure and handles one of the different kinds of effects in the signature, which might be state actions or reader or non-determinism or some other effectful operations that you could do in there. And that each handler will cancel out some of those. It will take them away and replace them with the body of the handler, substitute them out. Having done that, you're then left with a smaller computation. That is to say, another free monad, but with a smaller signature. And so then another one, smaller signature again, because you've handled another effect from it until there are none left. And then the magic trick, the thing that I really, really love about Fusion for free is then having done this, you can prove a Fusion law for this chain of handlers composed together the same way as you might for folds, and then finally erase the free monad altogether. Simon.
I'm getting completely lost.
Yes, sorry about that. Beg pardon?
Do you have a sort of code that? Do you have some example code that would show this?
I do. Unfortunately, I don't have any good way to show it to you this morning with the slides and all.
Okay.
Apologies for that.
So I guess I'm not getting it at the moment.
Well, I think then let's just focus on the key point being that Fusion for free is a pretty great approach, and I encourage you to read that paper, first of all. But second of all, that this was really important for us to be able to use this in practice. We had made some headway with getting this into production beforehand, but before we had dealt with the efficiency problems, we were still in on the order of actually I cannot remember the figures for how many requests we were able to serve, but I do know we were timing out on the vast majority of requests we were making as a result of that. So Fusion for free made things more efficient enormously. That was the point at which we had fused effects. That's when we started calling it fused effects rather than, well, we had actually made a new repository by then, but that was the distinction that we considered worthy of a new name, was that this is no longer based on the freer approach, it's based on the Fusion for free approach, and that we were extremely happy with the result of that in terms of the performance of the resulting artifact. So yeah, the mechanism of how that worked, Simon, to your point, I'm probably not going to be able to communicate particularly clearly this morning, and my apologies for that. But yes, again, I am happy to refer you to the paper. It is a beautiful read. And it kind of, I have one of these items here is folds in Fusion, and so perhaps that was a bit ambitious of me to include there. But the one of the joys of this, programming in Haskell in general, is the application of functions to values and returning of values from functions. And that sounds like a really trivial thing to say, because isn't that just what functions are? But coming from a background in doing imperative programming in Objective-C primarily. So Objective-C, by the way, if you're not familiar, is C with some object-oriented extensions, was developed in the 80s, primarily used by Next and then by Apple, and continued to be used into the mid-2010s for Mac and iOS development. It is since been superseded by Swift, not replaced, but like they're trying to push away from it. But dealing with C and its challenges, plus object-oriented programming and its challenges, kind of left me, I don't know, I guess ripe for working with Haskell. That's the setting that I was in right immediately prior to my work when I started using Haskell professionally. And so it was a breath of fresh air to me to come to a place now where I can just pattern match on data, and I can just return values, and I don't have to worry about the side effects, which is kind of funny given the title of the talk and all. But the distinction there is actually really important, isn't it? Like, The kind of effects we're talking about in C are not the same kind of effects we're talking about when we're talking about the state monad. The state monad isn't changing anything in memory. It's not mutating. It's simulating a mutable variable. It is not a mutable variable, which means that I can backtrack it. That's kind of cool. That's not something I could do with an IOREF, for example, or at least I might be able to, but not without doing extra work to encode that. Likewise, if I'm trying to do any kind of backtracking in C, I've got to roll up my sleeves. I got some work to do. That's going to be some effort. So looking at the handling of effect in general through that lens of just matching against some data types that say, you should do this. You should get the value of a mutable variable. You should put a new value into this mutable variable, or you should, split the computation into two non-deterministic branches or some other action that you want to take. That's a pretty cool thing to just be able to do within the language. And again, Haskell is a very programmable language. And what I mean by programmable is essentially that you have the ability to encode control flow in the language as just a very direct operation. Now, sure, I can switch on some variables in C on the values of some expressions in C and say, well, if it's this, I'm going to do this other thing, and so on and so forth, and encode control flow by something eerily akin to defunctionalization. But you don't. That's not how C is written pragmatically. Well, actually, I shouldn't say that. I don't think there's any one way that C is written. I think everybody has their own unique and beautiful C for themselves. But the challenge for me as somebody working on, again, primarily Mac and iOS development was interoperating with those environments. How do I write code in a way that I can maintain? How do I write code in a way that I can understand? And how do I deal with the fact that sometimes you just need to do interesting control flow, and that's a lot of work? Well, Haskell makes it a lot less work than it would have been elsewhere, and it's one of the reasons why I fell in love with the language to begin with. So I think another reason that I fell in love with Haskell, probably this applies to more than one person in this room, is types. I'm very fond of the idea that my compiler also knows what type a thing should be. It's not just me carrying that idea around in my head and hoping that I got it right. I really, really, really like having the machine check my work on that. But we're kind of sloppy with that sometimes. I mean, I can always just make a big data type that's got a case for int, a constructor for int, a constructor for string, a constructor for, every combination of particular types that I might have for some value. And I've done this for, this is the result of my evaluator. It's going to be a big type called value, which is a big subtype of a whole bunch of constructors for all of these different cases. And I lose a lot of type safety that way. And well, we have GADTs to deal with that sort of thing. That's pretty cool. But if I look at my computations, I'm doing the same thing if I say IO. I'm saying IO of A, well, it's doing something to produce an A. I actually care about what a lot. For example, if you give me a computation and I have to run it in order to produce some result, and then use that to produce my result, I probably actually care a lot about what the action that you've given me can do. Yes, it's an IO action, but that means essentially anything. It can do just about anything the machine can do, which is very powerful. Also kind of alarming. If, for example, I'm implementing locking on the file system, which is something I really hope never to do again. But if I am doing that sort of thing, recursive locking on the file system, even worse, has some really fun challenges. If it's not recursive, even more so, because if you call my function in the action that you give me that's being guarded by this file system lock, it's pretty easy to deadlock this system. If, on the other hand, I have a way of saying, well, you can give me some computation that's going to be guarded by this file system lock, and I'm going to I'm going to run this computation, and it can do, lots of stuff, but it cannot do locking on the file system. I'm going to be in a much happier place as an implementer, as a user of this API, just knowing that it's ruling out a case that I really don't want you to get into. That's kind of a clumsy example off the top of my head, but certainly there are a lot of examples in work that I've encountered where you want to be able to say qualitatively, this is the sort of thing that I want this to be able to do, that I want you to be able to do, when I'm going to run this action within some context that I care about the bounds of, for reasons like, bookending with taking and releasing a lock, or so on and so forth. So I'm keen on that sort of case because, again, simulating effects gives me a good way to talk about that sort of thing. Well, actually, it's not the simulating of effects specifically that gives me that. It's the fact that I can talk about what you can do in this computation. You're not just saying, well, you can do anything. This is I/O and it's all fair game. You're saying you can do this specific set of things. It'd be nice if it were convenient to say you can do anything that the calling context of this whole thing can do except X. That's not something that I can think of a convenient way to do in fused effects, for example. I think I can figure out a way to do it that's going to be really inconvenient and annoying to use, but I can't think of like a good way to express that. But that's something that the folks who work on Frank have talked about with masking of effects, for example. So that's another kind of cool thing, is that fused effects has benefited not just from work done within the Haskell community, but within the larger functional programming and programming language theory community as a whole, because there's work like that being done all the time, and some of that work is just has such a different perspective on how you should think about effects in that language, that like you're guaranteed to come away with a broader understanding of what you're doing in an entirely different space, simply because you will have that parallax from the different contexts. I don't know. I love that sort of thing. So I mentioned the principle of least privilege on the slide here as well. And this is closely related to the idea of saying, I care about what set of actions can occur in a computation for it to produce some value. If I'm writing a bit of code that is okay, so I am not a number. I am a free variable. Connor McBride and James McKenna, is that right? Yeah. Thank you. Excellent paper. I adore that paper. One of the really fun patterns that they use is to make these little pattern matching combinators that use alternative to say, the alternative type class to say that a match has succeeded or failed against some specific syntax constructor. So it's like taking a case and just reducing it down to, if it's lambda, then pure whatever, otherwise empty. So it ignores all of the other cases. It's like half a prism, I guess, is another way of looking at that. And those, in an effectful context, and I think it's perfectly reasonable to think of alternative and similar type classes as being like effectful interfaces in the algebraic effect sort of sense. They give you a really cool lens on computations like this, and the thing that code is not doing is saying that it returns this value in maybe. Because it's using alternative, it's therefore adaptable to lists, to binary trees, to other kinds of collections, to non-deterministic contexts, any of which might implement and have an instance of alternative. That's kind of a great thing. I mean, I'm saying basically polymorphism is cool, and yeah, that's true. Polymorphism is cool, but it's more than just that polymorphism is cool philosophically. Maybe that's not exactly the word I mean, but if looking at this in the abstract, it is making the minimum guarantee that it requires to do its job, or almost the minimum, which is to say, not I need this specific layout in memory. in order to return this result, but rather I need this method. I need to be able to make an empty thing and a non-empty thing. Alternative is slightly larger than it actually needs for that role. It also encodes choice, but if you ignoring that for the moment, for the sake of the illustration, it's a pretty cool construct to have available. And by saying only very precisely what it means, that's how it gets the ability to be adapted to other contexts without having to write a bunch of manual glue code. That is the principle of least privilege for those who aren't like, who don't call it to mind automatically, is the idea that something should ask for and receive the minimum set of capabilities necessary for it to do its job. Now, why? Because if you give it more capabilities than that, it either is wasting them, it can't use them, it's not going to do anything with them, or something may have co-opted it and will take malicious advantage of it, or accidental advantage of it, and delete your file system. Well, why did this thing have access to the file system? It was supposed to send an email via some abstract interface, but I gave it access to the entirety of the file system as well, plus my contacts and so on and so forth. And having these extra privileges, the only thing it can do with them is abuse them. So the principle of least privilege is a really important idea for security, for engineering in general. I think often that software engineering isn't really an engineering discipline, and it doesn't have very many or even any actual principles or laws, but the principle of least privilege is actually like a counterexample of that. It does have at least that one. There are a few others that everybody seems to look at and think, yeah, no, I don't actually have a good counterexample for this. And if anybody does, that'll be a pretty interesting discussion, I'm sure. But the idea from an InfoSec perspective seems to be pretty sound. And applying this within my work, I want to be able to say, this is the minimum set of requirements necessary for me to do the thing that I'm trying to do, and make no further claims, because I'm documenting what I'm trying to do very precisely. I'm documenting how I'm trying to do it precisely enough to get the thing done. I'm additionally telling you a really important piece of information if things are designed a little clumsy and you're getting here's a whole bunch of constraints and requirements that you didn't think that you should need to give me for this. Maybe that's a sign that I'm not abstracting things in the right places and that there's something missing, some layer missing in between somewhere. That's been a signal I've encountered from time to time. And ultimately, you're giving a valuable signal to the type system, the type checker, to your colleagues, etc., of very precise boundaries against this. It makes it more modular. I'm pretty fond of modularity personally. So the principle of least privilege is quite an interesting, quite an important topic in software engineering and computer science in general, in my opinion, and doesn't get enough attention in terms of actually applying it in pragmatic software engineering practices. Sam?
So I guess I agree with you, but and I think one of the examples of this that you might be alluding to is having an effect type system that constrains what you're allowed to do. And in general, adding for various forms of typing allows you to enforce this principle of least privilege statically. But my question is whether you personally have run into difficulties with using these type systems. So, for instance, and one example of this might be unchecked exceptions, and in a language like Java, that can be checked exceptions, that can be a big pain.
Sure.
And often in practice, we want to avoid or relax these kind of typing restrictions because they get in our way. So I'm wondering whether you ran into any difficulties with tracking kind of too much information.
Yeah, that's a fantastic question. Thank you. So I have seen the sorts of cases people are talking about where they look at that and they're like, this is just an unfair burden to place on the developer. It's tracking too much, etc. I almost uniformly disagree. I actually think that we are being too lenient on developers and we need to punish them more. But more precisely, we need to make it not punishment. So one of the lovely things about an effect system is, so using error as the example. So error is like either lifted into an effect, right? You can throw an exception or not. Throwing an exception is like the minimum interface of this, and then you might add catching exceptions as the extension of that. It depends on how much you are trying to do with that particular interface. In fused effects, we actually split error into throw and catch, and then error is the sum of them. So if you have an error handler that's backed by either, for example, then ultimately you're going to return an either. And one of the consequences of having too much information or trying to spread this sort of thing too thin is that you might have one kind of exceptions thrown here. So say in a compiler, in my compiler for my effectful language facet, which does not work, you might have unification errors as one kind of error. You might have type checking errors, kind checking errors. You might have a variety of other sorts of errors that can occur. Name lookup errors might be another one. And having them split into different types might just be convenient because you have these defined in different modules and you want to reduce coupling. You don't want to have one error module with one error type to rule them all and everything pulling it in from there because it makes everything really tightly coupled to this. Well, if I have 5 error effects to deal with the 5 kinds of errors, each individual position of these 5 might only have to deal with one, but there will be some code that has to deal with the fact that it's like error unification error, error type error, kind error, blah, blah, blah. And it gets unwieldy pretty quickly. So don't do that. Don't do it that way, more precisely. Yes, minimize the coupling. Yes, make sure that things are modular, but use the fact that you have handlers available to you to take a slightly different tack at it. In particular, so I'm also a big fan of optics within specific boundaries, at least, and pretty broad boundaries, but still. Prisms in particular, I think, are magical and delightful, and everyone should get to know a little better because they're so lovely. But if you have one of the things that I've done in my compiler is to make a handler for error that uses Prism to project errors into some other error type. So I have at the root of the program, I can throw and catch errors of whatever variety. It's just some error variety that encompasses all of them. Then in each of these modules, I'm just using the local one, and I kind of fan out the one into the other using carriers that say, let's pull the unification errors out of the all-encompassing error. I'm going to call it error for the sake of not being able to pronounce it conveniently. So pull the type errors out of error, pull the kind errors out of error. So when something is thrown, it's injected back in. When something is caught, it's projected out, dealt with, injected back in. And I've used one interface, the error effect, for the whole thing. So that's very convenient. I don't have to deal with a 5-way nested either, which is something I prefer to avoid. The associativity of either is always a pain in the ass to write down. And the entire system is still modular, the only thing that has to know about all of these is the thing that would have had to know about all of them anyway, because it has to run them all. So you end up avoiding the proliferation of constraints, which gets really arduous. You end up avoiding the coupling, which gets really arduous and can be really destructive to the maintenance of such a system. I'm not going to claim that it's a perfect solution, but I will say I'm very happy with how it's worked out for me. And through the wonderful creature that is duality, you have the same thing going for state with lenses. So you can do the same thing by saying I'm going to project out and inject in some subset of the global application state, such that this chunk is used here, this chunk is used here, et cetera, et cetera, et cetera.
So, well, kind of echoing what Simon was saying, are you going to show us some examples of the use of fused effects? Or
No, I can't show stuff on the slides, but
no. I was just wondering if there's something coming up on later slides.
No, sorry, I've only got this is my slides so far. They're pretty beautiful.
Oh, this is your slide.
Yeah, I worked pretty hard on them, but but yeah, if anybody wants to catch me afterwards and look at some of this stuff, I'd be more than happy to.
Yeah, maybe if you could,
yeah,
well, provide some pointers to some of these things afterwards, that'd be very helpful.
Yeah, absolutely. So just so that it's audible for the stream, on my GitHub under Roberix, Facet is my compiler. You'll also find Starlight in there, which I'm probably going to reference sooner or later. It's a game, an OpenGL game, where I use effects pretty heavily. And then Fused Effects is github.com/fusedeffects/fused effects. So don't worry about remembering that if you're local or whatever. If you're listening on the stream, hopefully you caught that or can rewind.
And just maybe to refine my question.
Yeah.
In practice, when you were building semantic out of fused effects and so on, I'm guessing you must have run into occasions where you found that the effect type system wasn't quite capturing what you wanted.
No, not really.
It just worked.
So let me tell you about a couple of cases where we found no, this is really obnoxious. Why do we have to write things down this way? Only came in like personal projects. One of which is I've got my game Starlight, which I mentioned. Hey, prophetic. In Starlight, I wanted to have a command line flag that says either turn on tracing or don't turn on tracing, like leave it off. Similarly, timing. And selecting a handler for one of those cases or the others dynamically based on a command line flag, I could either just switch on that flag and run a completely different code path. But if you want to pass in a handler in fused effects, it's ugly to encode it. You're using quantifiers. You might be using quantified constraints as well, which is always a sign that like, okay, so this is either something that is like, I know I'm doing something interesting and weird, and is obviously going to require this kind of thing, or it's like I'm doing something wrong because it should not be this hard. And it felt like the latter. I can't quantify that, but yeah, that's how it felt to me.
So I think that's the kind of thing that would be much easier in a language that has native support for effect handlers. Yeah,
exactly. And that very much to that point, I feel very strongly that that's an artifact of our encoding of effects in fused effects and not intrinsic to the idea itself.
Thank you.
You're welcome. But yeah, I really enjoy that whole space of those problems, because they're generally an indication that I'm doing something wrong and have something to learn.
Hi, Rob. I just
Hi.
had two quick questions. So in terms of the principle of least privilege, is there something you'd say about how that's maybe ties in with what Hasklers often talk about purity and the advantages of that, maybe purity being like zero privileges? And then on the other hand, also with compositional semantics, I think a complication often that comes up when using effect systems, for example, like polysemy or monad transformers, is if you want to like reorder effects or you actually want to run the effects at some place, making changes one place involves making changes a lot of other places as well, and maybe you have to do these lifts when you're running effects inside of your do's. So do you have any thoughts about how to organize that properly, or what the system could be designed to make that easier?
So I'm going to address the first part. You're going to have to remind me about the second one because it's a little more in-depth. Is that all right?
Yeah.
Okay, cool. So the question about purity and the principle of least privilege is pretty interesting to me because actually I think purity is not really the thing that I care about. I was going to make a stronger statement earlier this week. I was going to say that I don't think you should care about purity, but I actually don't believe that anymore. I think somebody needs to. It's just not me. More precisely, though, I think that like purity, impurity is not as interesting a question as value or computation. And that distinction is not going to be as obvious in Haskell specifically due to Haskell's semantics, but in like call by push value or the mu bar, polarized mu bar system L, whatever the stuff in Paul Downan's dissertation is talking about, I forget the names of them. That stuff likewise makes this kind of refinement more visible between value and computation. But so do effect systems in a slightly different way. Purity, zero privilege to your point, is that's a fantastic way to put it. And impurity then is not necessarily just like this thing is IO of A, but can be like gradually more impure by the introduction of each additional effect. With it's important to remember that these are, of course, simulated. With that, though, there is also a qualifier on that. If you simulate something, simulate an effect like error, throwing means that you won't necessarily get a value back. You have ways to take the computation and return something other, return via a path that doesn't result in giving back a value of type A. So where you had error of string A, you run it, you get back either string A, for example. So you're not necessarily an A. So yeah, it is gradually more impure. And the more such you add, the less certainty you have about the final result. In the case of errors, you have potentially more and more and more and more alternatives that it could have been, rather than the final result value that you actually want to get back, ideally. Or in the case of state, sure, you get the value back, but it's been annotated with more and more and more context. So yeah, I think principle of least privilege, looking at it through that lens, pure computations as like a zero privilege model of this are pretty cool. And to that, I'm trying to think how to phrase this. The other piece of research from Nick and Tom that we take great advantage of in fused effects is monad transformers and modular algebraic effects, what binds them together. Nick, did I get the title of that right? Cool. Thank you, Nick. It's a really cool paper, and it shows an equivalence between the two spaces. And one of the ways you show this is that a pure computation, or like a value lifted into a zero effect context, and the identity functor are in correspondence, which makes some sense. The identity functor has no other alternatives other than just the value that it contains. If there are no effects, you can't do anything other than hold a value in it. So on one side, you've got identity, on the other, you've got this whatever you want to describe that computation as, but it has having no effect, you can't do anything other than just return a value. So it is pure, and that's like a really crystal clear example of the principle of least privilege, in my opinion, because you have it mapping directly onto identity, and it doesn't map onto anything else as cleanly. So the second part of your question.
Yeah, maybe I can say it more simply. So these effect systems, for example, monad transformers and polysemy, put a lot of work into making the interface to composing effects usable. Do you have thoughts about the state of that, or do you think like it's sufficient as it's done now, or are there complications you wish could be solved?
I don't have enough of polysemy paged in to comment, and I'm not sure what you're referring to in relation to like monad trans or whatever.
You implement these monad trans instances so that you can sort of automatically lift your effects up
yes.
a certain number of levels.
Yeah. I mean, the approach we take in fused effects is via a type class called algebra. Algebra gives you a way to describe a handler. It does this by saying, has a method that takes the appropriate bit of effect syntax and requires you to do whatever with it. It's called algebra because if you were writing this out as like recursion schemes or something, this would look like your F algebra and a catamorphism, blah, 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 blah. But the lovely property that it has is that because of the way lifting effects works out, lifting handlers through that works out, you don't end up having the n-squared instance problem that you have in MTL, for example, where you have to have, well, monad reader is an instance of monad state. If monad reader RM, no, reader TRM is an instance of monad state S if M is an instance of monad state S, and then repeat that for every other kind of class. And so N transformers M interfaces, M type classes, and you get this very large grid to fill out. So we don't have that problem. I do feel like it's a pain in the ass at the same time. I mean, we have via the scoped effects work, we have this lovely distributive law, which represents the continuation in a strange way that I still need to think about more, actually, because it's still percolating even after all this time. But the actual threading of some handler through any effects, any scoped effects in the tail of the signature. This is really hard to talk about at all without having something to point to. I apologize for that. But I feel like it could be better. I look forward to it being better in future, actually, because I think that it's not just that, oh, there are infelicities here, but like I think these are things that can be addressed. I just don't know how.
Rob, I've got a question. So your implementation of fused effects is essentially a library that allows you to describe effectful systems. And it's one of the things that we do in effect systems is we say in the signature which effects are in scope or which effects are in a particular program. So we say we're going to use state effects, we're going to use read effects, etc., all at the type level. And in the talk you did yesterday with Patrick, you mentioned that it was just impossible to encode all of those in a sensible way because you had hundreds of effects, and GHC would fall over trying to compile it, and so you used FastSum to sort of fix that problem. But actually, I'm just wondering to what degree it's Haskell that should change rather than trying to encode things in a kind of with a great big sum, for example. Are there any features of Haskell that you think should be changed, or something in the type system perhaps, or what kind of features would you want to see to make Haskell become more of an effectful language in the way you would want it to be? Are there any things that we should be working on that would be useful? So I guess my question is, rather than having made it a library, were there things that you were working around that you just wished, if only we had better support for X, then this library would be much easier to write with or work with?
Yeah, absolutely. Thank you. So one of the challenges we had, the thing that led to FastSum specifically, was we had this union type that came from extensible effects. And it's very cool. It's an open union of functors. You can throw stuff in there and project stuff out partially, like via maybe. And we had large sets of data types representing syntax. So we wanted to be able to join those all together in some kind of sum union. So we did this and found that the instances required to resolve against that, to inject stuff in, project stuff out, were taking forever to compile because of a couple of known GHC issues. coercion pileup and some other kind of pileup with recursive constraints. And our workaround was this unrolling. So that was definitely us working around a problem that we had encountered, like a real problem we had encountered. But it was also like we encountered that real problem because it wasn't easy for us to just write down A plus B plus C plus D at the type level. It wasn't very, very convenient for us to actually say from this n-ary list of things, throw all these into a sum. It can be any one of these, and now I want to be able to do like an exhaustive check over them without the syntax becoming like really crushing trying to do so. So yeah, there are absolutely things like that would have made it easier. But it's also not clear to me that the sum-based approach that we were taking to effects was actually the right way to do this globally. Like, I think Alexis King's work on this has involved a really neat dual approach, passing around an n-ary vector of handlers instead. So it's a v-table essentially at that point. It's like passing a dictionary around. That's literally the approach that I want to take if I'm compiling this. Why don't I encode that in Haskell as well? Well, I've got a couple of experiments of that nature, none of them nearly as sophisticated as Alexis is, to be clear. But again, like one approach or the other still seems like I'm trying to do the wrong thing. To some degree, I want to be able to have open variants, open records. I'd like to be able to say, here's just a bag of stuff. I know what I mean. Why don't you know what I mean in terms of injecting stuff and projecting stuff back out? Plus, if I can actually give evidence so that, yeah, why don't you know what I mean is actually a reasonable question, then sure, that seems like a reasonable expectation on my part. Plus, I want it to be fast. I want it to be really, really, really fast to pull stuff back out. And that's not necessarily something that I can do on my own, but I think the runtime could. Additionally, we are very fortunate in that Alexis's work on what's the word starts with D? It's delimited. Thank you. Delimited continuations. Delimited continuations. Alexis's delimited continuations patch has landed in GHC, I think, this week, which is pretty spectacular. So that opens up another whole avenue of approaches to this, because you can take the mono-transformer approach like Fuse Effects is doing, or you can take the Dilemma CC approach, and both of these give you a path to implement the control necessary for effects. So yeah, pretty cool set of capabilities. John first, and then sorry. Oh, I'm sorry, I didn't see the mic. My bad. John first.
Okay, I'll ask mine. So I have a question about code evolution.
Yeah.
You're talking about the principle of least privilege, and this means that types give you very precise information about which effects are used. I'm sure that sometimes you realize as code is evolving, oh dear, I need to use another effect here that I didn't initially anticipate. And that may affect the types of very many functions, and you may end up making very many changes to the source code as a result. So there are ways you could mitigate that, of course. You could rely more on type inference for some of the functions. You could use partial type signatures, perhaps, and that lets you put an underscore somewhere. Or maybe you could use type synonyms or context synonyms to reduce the amount of work. Of course, if you use synonyms and you reuse the same name in many places, that might encourage you to give less precise type information. So there's a whole bundle of issues here. I wonder if you can say something about how you found the best way to work with the code is in order to trade off precise information against easy code evolution.
Yeah, absolutely. So this is a real challenge, and some of that challenge already exists anyway. Like if I change the result type of something, and that thing is part of a mutually recursive set of families, yeah, all of them are going to have to change the result type, obviously. Like that's just how this works. Okay, no big deal. I don't mind from that standpoint as a developer. I need another capability. Even if I only need it in one of these places, I view that as the cost of doing business. That's my take. It is a real penalty you pay, though. And if I, as you say, if I then say, well, I'm gonna make things a little bit easier on myself, I'm gonna use a constraint synonym, then I start getting warnings on stuff that doesn't use the extra effects. Or worse, if I, instead of doing that, well, I can't write this down. That's right. The membership constraints in fused effects are written as has whatever effect, sig m, where m is the monad that's going to be returned with, or wherever it occurs on the side of that. Sig is a fund up, so you don't generally see it mentioned anywhere else, but it has to be written there for performance, like compiler performance reasons. And so, Nick, to your earlier question, that also relates to it. I would love not to have to write the word sig every time I write one of these constraints. And the effect part of it, because of the way we've designed the membership constraints, you can actually write a whole bunch of different effects there. You can write has error foo plus state bar plus reader whatever, which is great, except that then if you use that constraint everywhere, which is a little bit tighter than doing has reader whatever, has state whatever, has foo whatever, you end up with a situation where GHC's redundant constraints warnings won't kick in at all. So you've solved the spurious or the reasonable but unwanted warnings by introducing spurious but unwanted constraints. And those ones then will tend to accumulate over time because you just keep adding things to those lists. You know, half a dozen of them could be unused anywhere in the system, and there's no way for GHC to tell you this because it has to work with what you've given it, basically. So again, I consider that an artifact of how we've encoded this, et cetera, but it's definitely an infelicity of the system, and it is a real annoyance to be like, well, finally, I've inserted the new membership constraint in the final position in what turns out to be in this file, and the other 10 that are now able to compile because they imported all have hundreds of these as well. That gets really, really annoying. That said, I also feel like that's a modularity problem in the sense of why did you design your system that way? I'm not saying you shouldn't have designed your system that way. I'm saying what forces brought you to this design. Can you re-architect things so that you don't end up with some of these problems? Is that a reasonable thing to do? So that's some of the questions I'd be asking myself. Ultimately, I feel like I have exactly the same problem when I'm adding parameters for exactly the same reason, though. And yeah, you see it very, very clearly through the lens of like, oh, and this must therefore pass a dictionary around. But the problem is one and the same, that I have some extra information, the availability of this capability to shunt around. Well, of course I'm gonna have to then do the plumbing. And it's nice that the non-type signature part of the plumbing is done for me in that case.
So first of all, I guess I can put John down as an endorser for the partial type synonyms proposal that I will be presenting later today. So no. my question is, so you mentioned performance considerations of the framework itself, but there's also the water that we Haskell programmer fish swim in, which is partiality and laziness. And the distinction between values and computations is not really clear unless you try to rule these out. So if you think about the performance not of the framework, but of the actual individual program that uses your effects, have you ever wanted to have laziness and or partiality as an effect that you can track?
I would much rather both of those things be effects that I can track than have them be like default assumptions of the language, yes. Now that's not an opinion that I would have held 3 years ago, I don't think, 2 years ago maybe. It's something that I've come to mostly as I've learned more about call by push value and about classical logic, polarized logic, system L, bar, blah, blah, blah. I would love to see those be things that I explicitly describe to the type system rather than that are just built-in assumptions, because I do want laziness, and I frequently want laziness, but I want to see it. So you could also look at that as a principle of least privilege thing, in the sense that, like, I want to see more of these things written down explicitly. That's, again, very personal take. I strongly suspect that several of my teammates would strongly disagree, but that's me. I think I see a couple of questions, 3 questions.
Reverting to Nick's question about how one might improve the language to make some of these pain points easier, one thing it seemed like you were describing with these sum types that we talked about on and off would be if we had efficient built-in record subtyping, so that you don't need sort of these large ad hoc sum types that need their own encoding that you've written. Is this something that you feel is like a big missing piece of the Haskell language that would improve things? And do you have a preferred way that you think we could get there?
Ooh, big missing piece is pretty strong. Like, I do think that's a really cool idea. It's something I would like to see happen. I would have to read the specifics of the proposal to be able to comment more precisely. But I again, to next question, I think it might be asking the wrong question. Like, this is an implementation detail, ideally. If it's an implementation detail that is the right way to implement the thing I'm trying to implement, then fantastic. But I'm not certain that it is yet. I would really, really like to explore that question more, though, either way.
Hi. I think you mentioned yesterday about so you've been using extensible effects before fused effects, is that correct?
Yeah, that's right.
So you mentioned yesterday about one of the reasons you moved to fused effects was because performance with MTL was terrible, I think.
Performance of our implementation of extensible effects extended with effect handlers and scopes, so scoped operations, was terrible.
Okay, and you mentioned today that another reason was that you couldn't really handle scoped effects using extensible effects. Is that right?
With our initial implementation, yeah, it was not scoped at all.
Yeah. So 2 questions. The first is, are those 2 reasons related? Did one come after the other? And the other question is, do you need to use MTL at all? Could you just use a pure algebraic effects approach?
Oh, that's a great question. Yeah, so the initial implementation was a fork of somebody's implementation of extensible effects. Then we started just, throwing crap in there, extending it wildly. Then we needed scoped operations, it turns out. So we extended it with that. Then we found, well, that gets us far enough to notice how bad our performance problems are. So yeah, they're related in the sense that it allowed us to get that far. It's not at all clear that our extension of it with scoped operations was responsible for the performance loss. In fact, it was pretty sure, we were pretty clear that wasn't the case. I forget the last part of your question, sorry.
Do you need to use an MTL thing at all?
So we use transformers. Fused Effects provides instances for basically as much of the transformers package as possible. We do not use MTL except maybe incidentally if like a dependency uses it, that sort of thing. But we don't use it directly ourselves at all. No.
Okay, let me rephrase that. Do you need to use monads at all?
So we don't use a non-algebraic effectful interface to any monad transformers that I'm aware of. Incidentally, we're going to use either, and it happens to be convenient to build that either in a do block. We might do that sort of thing, but we're only doing it in very small cases like that, very little minor one-offs, really.
Okay, thank you.
I think that's actually a good indication of how successful effects have been for us. It's just that we use them as our use of monads, period.
I'm afraid I'm going to cut that off just because we're out of time here. Thanks very much, Rob. Let's give Rob a...